right, good afternoon, everyone. Thank you for having me here. It's really good to be in such a distinguished crowd. Just wanted to bring greetings from Barefoot Networks. Everybody at Barefoot Networks conveys their greetings to you. All right, so pardon me if I keep looking in the back. But anyway, let's get started. So if you look at any typical network system that is built today, it's built from a fixed function ASIC. And this is true especially if you're talking about high-performance network systems. And this is because in the area of high performance, fixed function ASICs have been able to deliver because of their pipelined architecture. But when you build systems using fixed function ASICs, you kind of have to start from the bottom. You have to understand what features that switch chip supports, and then go build your control plane. So let's say you're building a network, and you want a feature X, and that feature X is not supported in your fixed function system or ASIC. You know, bad luck. You have to wait for the next rev of the silicon. So if you truly want to build a network that meets your need, you should be able to describe what your switch or a router should do. And today, with P4 and P4 programmable ASICs, you can do that. You can describe exactly what you want your switch to do in P4, and then you compile it, download it to a P4 target, and then your switch or router will do the functions that you want it to do. A little intro into why fixed function chips are so highly performant. It's because they are built using a pipelined architecture. So there's multiple stages, and each stage does some specific processing related to a specific feature. Packets come in on the left, go out on the right, and they go through all the stages. They get their processing done, and you get high performance, predictable latency. And so far, it's been difficult to build a programmable device that can deliver this performance because of various limitations. But advances in process technology and also advances in other fields like digital signal processors, GPUs, now make it possible for network chips to be built in a programmable fashion. So if you take the same architecture, the pipelined architecture, and make each stage fully programmable, then you have a programmable packet processor that can deliver the same performance as a fixed function ASIC. So in this case, since the programmable pipeline does not know what to do, you have to tell it what to do, and that comes from your P4 program. Here, we call it switch.p4. You compile that program, you generate a binary, you put it on the chip, and then also you generate the APIs with which you can use your control plane to talk to your pipeline that's running in the chip. So now this truly puts the network owner in the driving seat, because they are the ones who describe what the chip should do, and they're automatically getting APIs. They need to control that pipeline, and you go build the network that you want. So what is P4? P4 is a domain-specific programming language specifically created for packet processing functions. So the syntax kind of looks like C, but all the constructs and semantics of P4 don't look anything like C. They look more like packet processing logic, right? There are things like tables, headers, actions, fields, control, et cetera, et cetera. So it's very packet processing specific, and it's a programming language that is built using open source and community efforts. So this is just a snapshot of few members in P4 language consortium. There's more members, and there's active working groups that are happening, evolving the P4 language, and also applications written using P4. So P4 started out describing packet processing behavior for high-performance switch ASICs, but then it also found application in things like FPGAs, NPUs. There's actually even a P4 compiler to a GPU, imagine that, written by a university in the US. There's also P4 compilers to SmartNICs. So it's finding applicability wherever packet processing functions need to be described in a high-level programming language. So this paradigm of a high-level programming language, compiler, and a compiler target is nothing new. It's been there in compute. It's been there in signal processing, machine learning, GPUs. They all have some kind of high-level programming language, a very good compiler, and then a compiler target. So in networking, this has been missing, at least in high-performance networking. So the idea with P4 and P4 programmable ASICs is to kind of bring that same advantage of a high-level programming language paired with a compiler and a target into the field of networking. So little high-level overview of Tofino. Tofino is one of the P4 programmable ASICs. It's built using 16-nanometer FinFET Plus process. It's got 4 pipelines with a traffic manager in between ingress and egress stages. Fully programmable using P4. The chip itself does not know any protocols until you load the P4 program onto the chip. It, of course, has a PCIe Gen 3 interface for your control plane, x86 processor, or ARM, or MIPS, whatever, to talk to this switch chip. So this is a little bit more deeper look at the actual block diagram of Tofino. It has 4 pipelines, like I was saying. Each pipeline has about has 1,600 gig ports, and one pipeline has 1 extra, so there are 6,500 gig ports. And there is a fully shared buffer in the middle, so you get the advantages of a fully shared buffer instead of segmented buffer. But it's pretty simple design, and the ingress and the egress pipeline are made of identical stages, calling match action units. So I'll go into it quickly. So the pipeline architecture is based on something called protocol independent switch architecture. It essentially has a parser in the front, followed by match action units, and then what we call a deparser in the end. So packet comes in. It gets parsed according to what P4 program you have written. If you said parse Ethernet header, it'll parse it. If you say parse IPv6 header, it'll parse it. And then once the parsed fields are available, they go through all the stages, and they're looked up in tables that you have described in your P4 programming language. So essentially, this becomes your chip. This becomes your pipeline. And you get the performance of a fixed function ASIC. So this slide is actually showing how a P4 program maps to different modules in your pipeline. So there is a parser description that is mapped to the parser, but the parser description takes definitions of headers that it needs to look at. And then the match action units themselves are hosting the tables that are described in your P4 program. So if you described a table called L2, that will actually get mapped into one of the tables in the match action units. So this slide is basically just showing you visually how a packet comes in, the headers get extracted, they pass through all the different stages, and then they get built up into a new packet and sent out. Right? So it's pretty straightforward. So this is an example mapping of typical functionality into the stages. So you wrote a P4 program to describe L2, IPv4, IPv6, and ACL functionality. They get mapped into the available stages, let's say this way. Everything is good. Now you want to add MPLS, so you have to find space for MPLS tables. So you maybe adjust the IPv4 and IPv6 address table size a little bit, and then MPLS finds a way. So now your pipeline can do MPLS. So it's as simple as writing a new P4 program to install the new protocol. So we have a couple of demos running outside. I'm going to describe them quickly. So one of them is called a packet and flow monitor. Since Tofino is fully programmable, we were able to implement a small piece of logic, which essentially counts, which has a counter for packets that are coming in, but this counter is based on the packet size. So at any point of time, if you want to find out how many 64 bytes packets are in the chip, you can pull this counter, and then you'll know this is how many 64-byte packets went through the chip. So we created a bunch of packet size buckets, and as packets are going through, we increment based on which packet size came in. That counter gets incremented. And we also do flow monitoring. So this one is essentially, as flows are going through the switch, you are counting how many bytes each flow is taking. So you take a snapshot, let's say 1 second of traffic. You'll get to know in 1 second in your switch how many 64-byte packets are there, how many 256-byte packets went through. And then you can also see how many flows are there and how much data each flow is using. So all of this is implemented in the data plane with no intervention from the control plane. So all the stats gathering is happening inside the data plane. And then we have a little thrift program just pulling the stats from the chip. So this is how the implementation looks. There's a P4 program that's compiled, downloaded onto the chip, and the APIs are generated from the P4 program, and the APIs are called using a Python script using thrift. It's pretty straightforward. It's running Open Network Linux with our compiler, the drivers, and this simple Python-based control plane. The setup looks like this. There's a server with a 40 gig port that's generating traffic. It goes into one port of the switch. All the other ports are in loopback, so you actually send traffic through the full pipeline at line rate. And while this is happening, you're counting the packets and the statistics for flows. So it's quite powerful. Then you can visualize it using some simple Python graph application. So here you see the packet size distribution on the left, and then on the right, you see the flow size distribution. So you can see here that there's a lot of mice flows, about 1K mice flows, and then few elephant flows. So this is all in like 1 second interval that you're able to see. This is the distribution of packet sizes and flows. So now I'll quickly go through another feature called in-band network telemetry. So this feature allows you to essentially embed metadata that you can extract from your pipeline into the packet itself. So as the packet is traversing these hops, it can actually get information regarding which rule it hit, how much time it spent into the packet itself. How much time in each queue, who else was in the queue. So all of this metadata information can be encapsulated into the packet. The packet will grow a little bit, but you will have this information with the packet. So you can actually take it out at the end and analyze it and visualize it. So show you a few, before I go to visualization, this is the P4 code that is used to embed these metadata fields into the packet. So it's pretty straightforward. I don't know if you can read it, but it's basically saying add a header with this field. So the field could be switch ID, ingress timestamp, egress timestamp. So you can actually create any header you want, and you can put it in places in the packet that don't disturb other switches that don't understand INT. There have been people who've insert an extra MPLS tag with all the metadata information. You can put it in VXLAN GPE. You can put it right before payload, whatever, right? So your P4 program will dictate where you put this information. But once you get to the end, you can actually extract all that metadata and visualize what happened with that packet. So there's an application called Deep Insight, which allows you to visualize the whole topology, and then you can see which switches are having problems. You click on the switch, you can see what flows are there, and what is the queue occupancy looking like in real time, how many bytes in queue, is there any packet drops, and you can actually go and look at the packet drops and see which packet got dropped. This is another view, but essentially, programmable forwarding planes are going to change how networks are going to be built in the future, mainly because it gives the network owners the ability to go change the behavior of the forwarding plane and put in features that they really need. If you look at fixed function ASICs, they have features that all the customers need, right? So it's not just one customer. So if there are 10 customers for a fixed function ASIC, and each one requires only 4, there's usually like either 40 to 24 or something like that, right? More number of features. With a programmable ASIC, you can actually create whatever features you need and use only those features. And because there is no penalty on performance or price or power, it's easy to kind of replace a fixed function switch chip with a programmable switch chip and build the network you want. So that's all I have. Any questions?
Thank you for the presentation.
You're welcome.
You said about in-band telemetry. Can it work if the network is non-uniform and in the network the intermediate devices non-barefoot exist?
That's a great question. So the question is about, can in-band network telemetry work in like brownfield deployments, right? Where you have a mixture of P4 programmable devices, and there are devices that don't understand, in-band network telemetry. So the answer is yes, because if you have, let's say, a P4 programmable device on both ends of the network, like let's say it's a top-of-rack switch, you can get information across the two top-of-rack switches. So the middle ones will not have any information embedded into the switch, but usually it depends on the network, but usually it's not too much is going on there. So you will lose some visibility if you don't have a device that understands INT, but you can at least get end-to-end information. If you put it in the right place. If there is a top-of-rack switch in 2 locations, you can get the first top-of-rack where it hit, and then the last one. Right? So yeah.
Okay, thanks.
Да, как нетрудно заметить, это уже началась секция вопросов и ответов по докладу Према. Я чуть-чуть добавлю от себя к предыдущему вопросу на тему мониторинга, когда не все устройства в сети поддерживают PFO. По крайней мере, по нашему опыту, определенные классы проблем с очень большой вероятностью наблюдаются только на определенном подмножестве устройства. Например, большая часть проблем, связанных с TCP-инкастом, которые как раз требуют очень детального мониторинга с высоким разрешением по времени, потому что все интересные события, они субмиллисекундные зачастую. Почти все эти события случаются на топ-оф-the-rack'ах. Их почти не наблюдается где-то еще. Так что даже если не все устройства поддерживают программируемости вот такие возможности, если их стратегически правильно расставить, то можно получить много пользы. И да, у нас сейчас будет некоторое количество вопросов из онлайн-трансляции. Если кто-то хочет задавать вопросы Прему, лучше на английском, но если что, переведем. можешь это сказать? Джефф еще может дать комментарий насчет работы в ETF, которая пересекается с этим.
С точки зрения энкодинга, в ETF есть номер документов, который определяет, каким образом эта информация должна быть энкодирована в пакете, VXLAN, VXLAN-GP, GNIF, несколько еще. То есть даже если имплементация сделана несколькими вендорами и имплементация соответствует тому, что IETF, так сказать, задокументировал, и Barefoot, так сказать, participate в этом всем, то оно должно работать мультивендор тоже. И я так думаю, что Broadcom и Mellanox тоже скоро покажут, что они это делают.
Спасибо. Вопрос из онлайн-трансляции. Являются ли PFO ASIC, реализующие PFO, на самом деле FPGA? Prem, from online translation, the question.
Sure.
Is PFO ASIC actually FPGA?
Oh, great question. When you look at the programmability, it looks like an FPGA, but it's not actually. This is an ASIC actually. So it's built like an ASIC, and it's got a pipelined architecture. You write code in P4, and then you compile and generate a binary. It's unlike FPGA. In FPGA, you write RTL, and then you have to do place and route, and you require a lot more hand-holding with an FPGA. With this one, it's more of you generate a binary, and then you load it on the chip. So it is actually an ASIC with programmable pipeline.
Thank you, Jeff.
Thank you.
Как комментарий от меня, конечно же, можно на ASIC накатить прошивку, на FPGA прошивку, которая будет реализовывать PFO. Точно так же, как мы можем накатить на FPGA прошивку, которая реализует какой-нибудь MIPS процессор, но это будет не очень эффективный способ использования ресурсов. Хорошо для каких-то лабораторных упражнений, но в продакшн это будет не очень эффективно, в том числе по тому, сколько это будет потреблять. Jeff, next question from online is: what is the performance of Tofino ASIC?
Performance
in megapackets per second.
Oh, I see. It's 5 billion packets per second. Yeah, so it's 5 billion packets per second. So you can run the chip at 1.25 gigahertz if you want, and so that's at every clock cycle, it is doing 1 packet. So that translates to four pipelines at 1.25, yeah.
I would also like to add that, if I remember correctly, your ASIC has rather large tables, so it's quite scalable in terms of lookup space.
Exactly. So each stage in the pipeline has dedicated SRAM and TCAM, and those are assigned using P4 program. So you can basically assign any of those resources to any table, and your compiler will figure out what's the best way to allocate a particular table to the hardware resources. So it's pretty scalable, yeah.
Thanks. And by the way, I guess you have some development tools on your laptop, so people probably can
come and take a look.
Session, come and see how your tools can figure out what will be the utilization of hardware resources. And so on.
Yes, yeah. Yep. Thank you.
Да, на всякий случай дублирую, что после сессии на стенде Barefoot можно будет пообщаться с Джеффом, посмотреть на само железо и на инструменты для разработки.
Thanks, Jeff, for this presentation.
Извиняюсь, Према.
Prem, thanks for this presentation. I have a question.
Yeah.
Actually, we have, on the one extreme, we have very high performance ASICs, true ASICs, but they are along with the high performance, they have a high cost. On the other extreme, we have the general purpose processors.
Yes.
This is not that effective, but much cheaper. We are from, in this line, where do we have the P4 programmable ASICs? So it's more about the economy of your solution.
Yeah. So that's also a great question, because I mean, just because programmability is available doesn't mean that it'll be adopted unless the economics get right, right? So the cost point for P4 programmable ASICs today is the same as a fixed function ASIC. So if you're using a 6.4 terabits per second fixed function ASIC, the P4 programmable ASIC should cost the same. And it's not because they're priced lower or higher or anything. It's more because we're able to fit the logic into the same area, die area, as a fixed function chip. So if you take any fixed function networking chips, the area is decided by the number of SerDes blocks. So these SerDes blocks are laid on the ends because that's where packets come in. And then in whatever area is in the middle is where all the logic and the memories get put in. So we were able to actually fit all our programmable logic and memories in the same area as a fixed function chip. So no extra cost compared to a fixed function chip. So yeah, so if you take NPUs and FPGAs, maybe they're costly. And then you take general purpose CPUs, maybe they're not that expensive, but the performance is not that high. The P4 programmable ones fall in the similar category as fixed function ASICs. Yeah.
I would also like to add that there is a great paper. It was presented at SICOM, I guess, about programmable pipelines.
Yes.
And in that paper, there is estimation of upper bound.
Exactly.
How more complex is programmable pipeline compared to fixed function one.
Yes,
and
yes.
difference is not that great.
Correct.
And besides that, a lot of the chip is actually lookup tables, memory, and so on.
Sure.
And you have to have them anyway.
Exactly.
So it's common part for fixed function chips and programmable ones.
Right. I think there's probably a 1 to 5% extra area that's needed, and in most cases maybe the same. And as process shrinks, like 7 nanometer and more, that difference will get even shorter. Yeah, negligible.
Thanks.
Yeah.
Есть ли у нас... есть вопросы.
Hello, could you explain what kind of control software we can already run on top of P4? Like
A control plane software?
What kind of control plane software?
Oh, sure. So the most popular one right now seems to be Sonic with Psi. But the interesting thing about that is Sonic and Psi don't take advantage of any programmability because Psi has fixed features and Sonic also has fixed features. But the advantage with Sonic is some of the mega-scale data center folk are able to take Sonic source, change some P4 code, and then write their own control plane app along with other control plane apps in Sonic. So due to that reason, it's getting more popular. We've also demonstrated, like remote controllers like Open Network OS, ONOS controller. There was a P4 plugin submitted to ODL recently. So that's available, Open Daylight. And we ourselves, Barefoot, we are working with IP Infusion. So that support will be coming soon. And there's other, control plane softwares that are coming. But in terms of like fully open control plane, I think Sonic and ONOS are the examples. Yeah.